Pluto is a far-off and baffling planet that was once an individual member of our planetary system's family. However, recent alarming declarations by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning revelation. They suggest that this icy world might be on a potential collision course with Neptune. But how could this occur, and what would be the results of such a massive event? Are we witnessing an intriguing galactic anomaly, or is there something more to this looming astronomical crash? Join us as we explore the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was downgraded to a dwarf planet, remains a subject of interest and study in the astronomical community. As indicated by recent forecasts by leading researchers, Pluto's orbit is perilously close to Neptune's, which has raised alarms from astrophysicists like Neil deGrasse Tyson and Michio Kaku about a potential dangerous collision between these two planets that could pose a tremendous risk to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution yet. But the interest doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, straying significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more unusual is its tilt of 17 degrees to the ecliptic plane. The path Pluto follows is much more extreme compared to the other planets, adding layers of complexity to its orbital mechanics. Perhaps one of the most captivating aspects of Pluto's orbit is its convergence with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contrary to what we might expect from their positions in the solar system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions of other planets. The study of Pluto's orbit began shortly after its discovery, as astronomers attempted to figure out its unique trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stands out with its steep tilt and elongated shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's, but the stability of Pluto's orbit amidst these complexities is a testament to the intricacies of space mechanics. The three-body problem in space refers to the challenge of determining how three objects, like Pluto, Neptune, and the Sun, move and influence each other through their gravitational pull. It's akin to predicting where these objects will go based on their starting positions and the way they interact gravitationally. For Pluto, this problem illustrates how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex manner. Key to this stability are phenomena like alpha libration and scope libration, as well as the VK oscillation, which are all part of this puzzle. According to astrophysicists, what keeps these planets on their orbits is a phenomenon known as alpha libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned no less than 90 degrees away from Neptune, ensuring that their paths do not collide. On the other hand, scope libration refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it gets closest to Neptune or another giant planet, it is positioned primarily above their orbital plane, adding an extra layer of protection from potential collisions. Another essential element in this situation is the VK oscillation, named after three scientists Bond, Zippel, Leo, and Kai who studied how objects move in space. This phenomenon describes how Pluto, Neptune, and the Sun's gravitational forces influence Pluto's orbit, helping to stabilize it over long periods. Despite Pluto's seemingly chaotic orbit, these stabilizing phenomena work to keep its path smooth and avoid a collision with Neptune. The VK oscillation demonstrates that, even when things in space appear to be wild and unpredictable, certain patterns and rules help maintain order. All these factors contribute to Pluto's orbital stability, preventing it from colliding with Neptune or veering off course. These interactions help us understand the dynamic nature of our solar system, shedding light on how even the most seemingly unstable orbits can reach a state of balance through complex gravitational and orbital mechanics. Recent computer simulations from the late 1980s revealed that, despite these stabilizing factors, Pluto's orbit is still somewhat turbulent. Variations in its initial conditions, have led to significant differences over vast timescales. However, these interesting properties of Pluto's orbit have been shown to maintain stability over extraordinarily long periods, effectively keeping the turbulence in check. These tests have also helped us understand how larger planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune, in particular, has a unique relationship with Pluto. Every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't alone in stabilizing Pluto's orbit. Jupiter's gravity also plays a significant role. Additionally, Saturn's gravitational influence helps as well. These tests indicate that Jupiter's gravity alone is powerful enough to ensure Pluto remains on a stable orbit for billions of years. It seems that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues its journey through space without running into any trouble. These gravitational interactions are crucial to maintaining the order and stability of our solar system. Without them, the dynamics of the solar system would be far more chaotic, with bodies like Pluto potentially crashing into others or being ejected from their stable orbits, triggering a chain reaction that could affect other celestial bodies. For Pluto, understanding its orbit is especially important in the context of discussions about its potential collision with Neptune. This knowledge helps us better understand the dynamic nature of our solar system and the mechanisms that keep it functioning as we know it. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to deepen our understanding of our place in the universe. Exploring the depths of space often forces us to confront the erratic nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in Pluto's position or velocity can drastically alter its long-term trajectory in the vast expanse of our solar system. Pluto occupies a unique position that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant revelations about its composition and behavior.
One of the most intriguing features of Pluto is its surface, which is a complex tapestry of ice, rock, and other mixtures. The New Horizons mission, which flew by Pluto in July 2015, provided rare data about this distant world. Pluto's surface is characterized by vast fields, towering mountains, and deep valleys. One of its most notable features is the Sputnik planitia, a large heart-shaped plain made primarily of nitrogen ice. This region showcases a variety of landforms, including massive ice sheets and what appear to be flowing glaciers. The presence of such features suggests that Pluto might still be geologically active despite its distant location from the Sun and its frigid temperatures. Another fascinating aspect of Pluto is its atmosphere, which is primarily composed of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is thin, but it exhibits intriguing seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior is a reflection of the complex relationship between Pluto and its environment. During its closest approach to the Sun, some of the gases in its atmosphere may freeze out onto the surface, while as it moves farther away, these gases sublimate back into the atmosphere. Pluto's relationship with its largest moon, Charon, further adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that both bodies are in a mutual orbit around a common center of mass, rather than Pluto simply revolving around Charon. This unique relationship contributes to the intricate gravitational dynamics in the region, affecting the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to numerous other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, providing astronomers with a glimpse into its formation. Pluto's orbital characteristics could offer insights into the migration patterns of these distant objects, suggesting that interactions with larger planets may have played a significant role in shaping their current orbits. One important implication of understanding Pluto's orbital features is the potential impact on our understanding of the solar system's evolution. Gravitational interactions with nearby giant planets like Jupiter and Neptune can alter the orbits of smaller bodies, including those in the Kuiper Belt. Such interactions could lead to shifts in orbits, potentially resulting in collisions or ejections from the solar system. As researchers continue to investigate the details of these interactions, they may uncover broader patterns governing the behavior of celestial bodies throughout the cosmos. The study of Pluto also raises philosophical questions about classification in cosmology. The decision to rename Pluto as a dwarf planet in 2006 sparked controversy and debate about what constitutes a planet. The International Astronomical Union's definition focused on criteria such as orbital dominance and size, leaving many to reconsider the implications of such classifications. This ongoing debate reflects our evolving understanding of the universe and underscores the need for a flexible approach to classifying celestial bodies. Additionally, the potential for future exploration of Pluto and the Kuiper Belt remains an exciting frontier. With advances in technology and mission planning, astronomers envision sending more spacecraft to study not only Pluto but also other distant objects that share its orbital traits. Such missions could yield valuable data about the primordial materials that shaped our solar system, possibly offering clues about the origins of life on Earth. The study of exoplanets, planets beyond our solar system, is another fascinating area of research that intersects with our understanding of Pluto. As astronomers discover more exoplanets, particularly those in the habitable zones of their stars, the lessons learned from studying our own solar system could inform theories about planetary formation and habitability. Finally, public interest in Pluto has endured, fueled by its mysterious status and the stunning images returned by the New Horizons mission. The dwarf planet has captured the imagination of people worldwide, sparking a renewed appreciation for the vastness of space and our place within it. As we continue to unravel the mysteries of Pluto and the celestial bodies that share its region of space, we are reminded of the incredible wonders that the universe holds. Pluto's unique characteristics extend beyond its physical properties and orbit. It serves as a critical case study for understanding planetary formation and the dynamics of celestial bodies. The formation of Pluto is thought to have occurred in the early solar system, alongside other Kuiper Belt objects, and studying its composition can shed light on the conditions prevalent during the solar system's formation, potentially illuminating theories about the development of Earth-like planets, including Earth itself. Recent studies suggest that Pluto may have a subsurface ocean, a discovery that could change our understanding of its geology and potential for supporting life. Data from the New Horizons mission revealed that some regions of Pluto's surface, such as its frozen mountains, may be made of water ice, which behaves differently from regular rock under low temperatures. This finding opens the possibility of liquid water existing beneath its icy exterior, raising intriguing questions about the potential for life, even in such extreme conditions. Furthermore, Pluto's relationship with its environment can provide insights into atmospheric science. The seasonal changes in its thin atmosphere offer a natural laboratory for studying atmospheric processes on a planetary scale. Scientists are particularly interested in how the interaction between solar radiation and the surface might create complex weather patterns, akin to those seen on larger planets. The importance of continued observation of Pluto and other similar celestial bodies cannot be overstated. As more missions are planned to explore the outer reaches of the Kuiper Belt, we can expect a wealth of new data that challenges existing theories and expands our understanding of planetary science. Each discovery adds another piece to the puzzle of our solar system's history and the forces that govern its evolution. Through these investigations, Pluto remains a symbol of our ongoing quest for knowledge about the universe, inviting both scientists and enthusiasts alike to contemplate the mysteries that lie beyond our familiar domain. As we continue to explore the outer reaches of our solar system, Pluto remains an intriguing object of study, offering new perspectives on planetary science and the mechanics of celestial bodies. Its classification as a dwarf planet has not dampened the excitement surrounding its mysteries. In fact, the ongoing exploration of Pluto, particularly through the New Horizons mission, has provided groundbreaking insights into its surface, atmosphere, and orbit, significantly enhancing our understanding of small icy bodies in the Kuiper Belt.
One area of growing interest is Pluto's potential as a window into the early solar system. The Kuiper Belt, where Pluto resides, is thought to be a preserved relic from the time of the solar system's formation. This region contains many other objects that are considered to be remnants of the primordial materials that formed the planets. By studying Pluto and other similar objects in the Kuiper Belt, scientists can gain valuable information about the processes that shaped the early solar system. These objects may hold clues about the formation of Earth and the other planets, providing insight into how life-supporting conditions might arise elsewhere in the universe. Moreover, recent research into Pluto's surface features, such as its nitrogen ice plains and mountainous terrains, suggests that this distant world may still be geologically active. This raises the possibility that Pluto could harbor a subsurface ocean, a feature that could potentially support some form of life. The discovery of a subsurface ocean, if confirmed, would represent a significant finding in the search for life beyond Earth, indicating that liquid water may exist in unexpected environments, even on small icy bodies far from the Sun. Another avenue of exploration is Pluto's interaction with its environment. As it moves through the solar system, Pluto's atmosphere undergoes changes that mirror seasonal shifts on Earth. The seasonal variations in Pluto's thin atmosphere, which are driven by its elliptical orbit, provide valuable data about planetary atmospheres. Understanding how Pluto's atmosphere behaves in response to changes in solar radiation could offer insights into the atmospheres of exoplanets, some of which may have conditions suitable for life. In addition to these scientific pursuits, Pluto's story also raises philosophical and cultural questions. Its reclassification from a planet to a dwarf planet sparked debates about what it means to be a planet and what criteria should govern such classifications. These discussions reflect the broader issue of how we define and categorize celestial bodies and highlight the dynamic nature of scientific discovery, where new information can challenge long-held assumptions. This evolving understanding of Pluto, its status, and its place in the solar system serves as a reminder of the complexity and wonder of the universe.